So in this example, I'm going to work through a typical conservation of linear momentum problem, and we're also going to see how it very often combines with the idea of the impulse-momentum relationship to find the force on a single object during the collision, and our ideas of energy to prove it's an elastic or inelastic collision. Okay, so let's go. So we have here this situation where initially I'm going to have the car A is initially headed downward, and it has a mass of 2.12 kilograms and an initial speed of 8.32 meters per second. It's going to collide with car B, which immediately before the collision it always has a mass of 1.39 kilograms, but immediately before the collision, it's headed at 10.2 meters per second at an angle 25 degrees with the vertical as shown. And then after the collision, you're told that car A is moving directly to the left at 1.74 meters per second, and we don't know what B does. Okay, so part A asks us to express the final velocity of B in unit vector notations. We need the x and y components of the unit vector of the vector velocity for B. So I'm going to draw in a standard right-handed coordinate system, x and y, and that's what I'll use throughout this problem. Part B, you can see, is find the force on A during the collision if time is 0.032 seconds. That's a different problem. That's a problem from the previous module on the impulse momentum relationship, but you can see how it ties in as a follow-up to a conservation of linear momentum problem very often. And then prove if the collision is elastic or inelastic, and that we need to find the total initial kinetic energy, compare it to final total kinetic energy at the end. Okay, so for part A, we're going to use conservation of linear momentum for this. So this is a collision. We're trying to find the velocity of an object immediately after the collision. But we have to do it in parts. So the best thing that we can do is I highly recommend that you always make this chart with initial and final, and then have X, and then leave space for a couple objects to be written. So that's why it's kind of wide or long, I guess, tall rows, and then Y. So I'm going to have two objects here. So my initial for A is going to be in the X direction. It's initially headed downwards. So the mass of it would be 2.12 kilograms, but in the X direction, the initial velocity is 0 because it's initially headed in the negative Y direction. And then for the Y direction of that, we need to put a negative sign. Be very careful with your negative signs, and it's going to be 2.12, the mass, times the velocity, which was 8.32 meters per second. The negative sign is very important because that shows that it's headed in the negative Y direction, and that's going to matter because momentum is a vector. So then for the X direction, for B, we can see that it's going to have an X direction that is going to use sine of 25 because it's opposite of 25 degrees. And my X direction initially is going to be headed negative towards the left. So it's going to have a negative times its mass, which was 1.39 kilograms, times the speed, 10.2, times the sine of 25. So now I've taken what we know about vectors and just taken the X component of its velocity vector, which is what I've shown here. And then the Y direction for B, we can see that it's going to be positive because the Y velocity is headed up. So I'm going to have positive times the mass, 1.39. So I'm writing down the momentum terms. And I suggest leaving them like this. Don't multiply it out in your calculator or anything. That way you can find mistakes. So 1.39 times 10.2, and then the Y component is adjacent to 25 degrees. So cosine of 25. So those are my initial momentums of the system. Now, the final momentum, well, remember that we're told A. They don't stick together. So A now is going to have its own momentum, and it still has the same mass. And it heads in the negative X direction. So it's going to be negative 2.12 times that speed in the X direction, 1.74. And again, I put it as negative. Now, because it's headed in the negative x, there's no y component. So the y direction would just be 0. So this would be here simply 2.12 times 0, because there's no y velocity of a at the end. Now, here's a trick that you need to keep in mind. Your unknowns are going to be in this table. What you're trying to find will be in this table, and you're going to leave them in components. So if I want to find the velocity of b, then what I'm going to do is write down the mass of b, 1.39, and then I don't know its final x velocity. So I'm going to say v final in the x direction of object b. And again, the subscripts can be really important. Start practicing using them. However, you do need to denote that it's the final velocity in the x direction of object b. That's going to be what you need to have in there. So that's going to be one of the things we need to solve for. That's one component of the final velocity. The other one would be 1.39, and then v final y b, the final velocity in the y direction of object b. So those would be my two components. If any of them come out negative, that's going to be because that's going to be negative in the x direction or negative in the y direction, and that's okay. So I want to solve for v final of object b, which is going to be equal to v final x, and then that'll be in the I hat direction, and then plus v final y in the j hat direction. So that's my end goal. So all I need to do now, and the reason that organizing every single conservation of linear momentum problem with this table is going to be because what I can do is I'm going to take the sum of all of my initial momentums in x, and I'm going to set them equal to the sum of all of my final momentums in x. So my initial momentum, the first cell in the upper left, is going to equal my final momentum in the x direction. And I'm also going to have an equation where I set the initial momentum in the y direction equal to the final momentum in the y direction. So I'm going to add up both those terms. So let's see what that's going to look like. So for the x direction, then what we're going to have is I'm going to have 2.12 times 0, so I'm just going to put 0, and then minus 1.39 times 10.2 sine of 25 is going to equal negative 2.12 times 1.74, so that's the first term, and then plus 1.39 v final xb. And you can see that that's our only unknown in that entire equation. So what I can do then is just solve for v final x, for v final x of object b. And what I should end up with is negative 1.66 meters per second. So it is negative, which makes sense given the way the collision goes. And that's going to be one of my two components for that final velocity. So now I'm going to do the same thing in the y direction. I'm going to take the sum of my initial momentum, so those two terms added together. So minus 2.12 times 8.32, and then plus 1.39 times 10.2 cosine 25 is then going to be equal to my other two terms added together. In this case, one of those is 0 because A had no momentum in the y direction. So 0 plus 1.39 v final yb. And again, that's my only unknown for the final velocity of object b in the y direction. So v final yb, then I can solve and I get negative 3.45 meters per second. And that gives me my final velocity in the y direction. I can combine that, and then now I can just write out my answer. So what I have here then is that V final of object B in unit vector notation would be negative 1.66 I hat minus 3.45 j hat meters per second. And that is going to be my final result for part A of this problem. That is applying conservation of linear momentum to the situation and finding the two components of the velocity. If it had asked for a magnitude and a direction, I would have done all of this. And then I still would just have the additional step of saying, okay, I have my two components of a vector, find the magnitude, the square root of the squares, and the angle, the inverse tangent, just like we've always done with all of our vectors. Okay, great. So now let's go ahead and look at part B of this problem. We want to find the force on object A given the time of the collision. So this is where you need to keep impulse momentum separate from conservation of linear momentum. So for part B, it's important to note that conservation of linear momentum is an entirely different problem-solving technique than impulse momentum. Right? Conservation of linear momentum involves the entire system. You're looking at the total momentum of the system, and you're telling the initial equal to the final. For impulse momentum, remember it applies to a single object in that system. So in this case, we need to use impulse momentum to get the force on a single object. So to remind us, we would have here that the average force, right? And in this case, we want it on the 2 kilogram mass. So the average force, on not the 2 kilogram mass, the 2.12 kilogram mass, so object A, I'll call it. The average force on A times the time, that's going to be my impulse, is equal to the change in momentum of object A, just a single object, not of the system. The change in momentum of the system is 0. So the change in momentum of A. And then we do this in X and Y. We need to have an F component, so F average will then be equal to F average X and F average Y. We have an X component to our force and a Y component to our force. So this is basically a review of the previous module, but now seeing it as it often shows up as sort of a follow-up to a conservation of linear momentum problem. So we can write this out then, and we can say F average in the X direction on object A will equal the mass of object A, because that's the one I'm trying to find the force on, times V final, and let's do this, and this is in the X direction, of object A, minus V initial in the X direction of object A. So again, your subscripts are your friends. They are there so that when you write a variable down, you know what it talks about. So that's going to be my change in momentum, and I divide that by time, and I'll be able to get my force. So if I go ahead and I do that, then I have the mass of object A is 2.12 kilograms, the only mass I use in this process. Then V final of object A, well, that was given actually in the problem, right? That was going to be my 1.74. So that's going to be 1.74, and it was headed to the left. So I need to make sure to keep that negative sign there. So negative 1.74 minus, and then the initial momentum, it was initially heading straight down. So the initial momentum in X was 0. And then over delta T, the time was given in the problem, and it was 0.032 seconds. Often you have to convert from milliseconds to seconds here. And so when I do that, I end up with negative 115 newtons, and that's going to be in the I hat direction. That's the X component of the force, and now I need the Y component of the force. So F average in the Y direction on A will again be equal to the mass of A V final in the y direction of object A minus V initial in the y direction of object A, all over delta T. Just be very careful as you're writing all these things through. The worst thing you can do is mix up X and Y or initial and final. You need to keep track of all of these terms. So the more labels, the better. All right, so 2.12 kilograms, V final in the Y direction of object A. Well, remember, it had none because it was headed directly to the left. So just 0, and then minus, it was initially headed straight down with a speed of 8.32. So be careful with your minus sign. So minus a negative 8.32 all over 0.032. You solve this and you get positive 551 newtons in the J hat direction. Those two combine and give me my average force on object A. Oh, sorry, 551 newtons. I wrote it down incorrectly. So that gives me my average force on object A during that collision. Okay, so if we go back up to our original problem, we have now found the velocity. We've done part A. We found the velocity of B in unit vector notation. We found the force on A. We left that in unit vector notation. If you're not told, then just go ahead and do that. And then I have to prove if the collision is elastic or inelastic. So we need to compare the total kinetic energy initially to the final kinetic energy. So for part C, to prove elastic or inelastic, compare the sum of all the initial kinetic energies. Now this is a scalar to the sum of all final kinetic energies. If they're the same, then it's elastic. If you've lost energy, then it's inelastic. So let's see how that turns out here. So the sum of all initial kinetic energies would be 1/2 times the mass of A times the speed of A, the initial speed of A squared. So no X's and Y's here. We're dealing with energy. Energy has no components. Plus 1/2 times the mass of B times the initial speed of B squared. So again, I'll make those as speeds. And so if we go ahead and we look at this, then I'd have 1/2 times 2.12 kilograms. And the initial speed of A, well, it was only headed in one direction. So the speed we were given was just 8.32. So 8.32 quantity squared. And then plus 1/2 times the mass of B, and B was 1.39 kilograms. And then the speed was 10.2 at 25 degrees. We don't care about the 25 degrees anymore. It's just the speed was 10.2. So 10.2 quantity squared. So I can then calculate my total initial kinetic energy, and I will get 146 joules. I'm going to box that. It's not my answer, but it's part of where I'm going to use to support my answer. So then I'm going to look at the sum of all of my final kinetic energies. So 1/2 times the mass of A times V A final squared, again speed, plus 1/2 mass of B, V B final, the speed squared. So 1/2 times 2.12, final velocity in A, that was given in the problem. It went to the left at 1.74. So 1.74 quantity squared plus 1/2 times the mass of B, so 1.39. And then we need to have the speed, right? So the speed of B. So VB here, final, quantity squared, that's going to be the speed, which is equal to VBX final squared plus VBY final squared. So we had our x and y components in unit vector notation. So the speed then will be the magnitude of that vector. So to remind us, it was negative 1.66 squared, and then plus negative 3.45 squared, square root of that. And if you work that out, then you should get that the speed is 3.83 meters per second. So that's what I would use for my final speed when I do this calculation. So now we can see that I have clearly lost energy, right? So K, the sum of all final kinetic energies is less than sum of the initial kinetic energies. So this has been proven to be an inelastic collision, and that is my answer. All right, so there are a lot of parts that can go into this, and you have to keep your algebra straight as you work through these problems. Remember whether or not you're using conservation of linear momentum, and then make the table. And then if you're going to use impulse momentum to get the individual force, just be careful about which object you're talking about. And then to prove elastic or inelastic, just sum up all of the scalar initial kinetic energies and add and compare that to the final kinetic energies. That's a conceptual idea of looking at your total kinetic energy initially and comparing it to the final kinetic energy. Okay, let me know if you have any questions.